Okay, so this is kind of like the application of this. Let's see. So you have poor unfortunate Xbox 1 stuck on a ramp with a rough surface. Okay, so you have, what you're going to have is an angle, theta. All right, the Xbox is going to have a mass of m. Okay, and it is no acceleration. This is static. It's stuck on the ramp. Acceleration equals 0. And so you would want to find the coefficient of friction. And since this is 0, this is going to be the coefficient of static friction. You don't really have to, if you've already stated that it's still, you don't really have to put the s there. I'm just letting you know. I'll probably not put the s there in this problem since we already kind of defined what we're talking about. So anyway, let's go ahead. First things first, let's draw a real free body diagram first. So you would have your weight, and you're going to have your normal force, which is not going to be as much as your weight. Okay, let's see, about like that, maybe a little bit more. I'll just make the arrow longer. Okay, so that's your normal force. All right, and then since it's like stuck on the ramp, you know that you're going to have your frictional force going up the ramp. All right, so that's your real free body diagram. Now I'm going to draw the pseudo free body diagram. I'll draw this kind of dotted line to indicate that I have a surface. So we know we'll have normal force. Okay, so I'll do weight and then normal force. Okay, and then we're going to do the frictional force. Now, let's see. You know that you're going to have something balancing out your normal force, and also you know that you're going to have something balancing out your frictional force. I kind of did this one in a weird spot. Got some kind of arrow type thing here that would be what's pulling it down the ramp, but the friction's like, no, it's stopping it. It's pulling the other way. I'm actually going to move this arrow, and this is kind of what I've been doing to create the triangle. In case you didn't know that, I'm going to move it. It should be a dotted line, but I'm going to move it down here. That's just this arrow. So let me erase that real quick. So I'll just move that down there. My dog is not happy about this. Anyway, so most of you should know that these are just components of your weight, and that theta, it's the same theta as this up here, actually goes up closest to the object. So this line right here, coming down, that's balancing out your normal force, is going to be your weight, cosine, because it's closest to the angle, weight, cosine, theta. And then this one down here that's pulling it down the slide is going to be your weight, sine theta. All right, and you know that your acceleration is 0. It's weird, that kind of deleted that. All right, so I wanted you to find, or we want to find mu, your coefficient of friction. And remember, the equation for your frictional force is, I'm not going to bother with the s, is coefficient of friction times your normal force. Let's go ahead and solve for this. Okay, so therefore, just divide by normal force. Therefore, mu is going to be equal to your force of friction over your, over your normal force. Well, actually, I should have said to answer this in terms of mass, any fundamental constants, which the only one we've really dealt with is your acceleration due to gravity or your gravitational field, and theta. So your answer is going to be in terms of these things. So this won't work because you got your forces. So let's look and see. Do we know what frictional force is? Well, frictional force points up the ramp. Do we have anything that's the same amount that's holding this on here that is pointing the opposite way? Oh, look, we do. Those two are acting opposite of each other, and they're basically canceling each other out because your acceleration is 0. So since your acceleration is 0, don't forget you always on these want to write net force equals mass times acceleration, your mom version of Newton's law. Okay, so there you can say, therefore, your net force overall is equal to 0. Don't make that assumption. Always write this. If you're, always make sure this especially. So anyway, then you can say, therefore, the magnitude of your frictional force is equal to, well, that is weight sine theta. And I always do magnitude on things like this if I can see which direction they're going. All right, so that's the magnitude of your weight sine theta. Okay, and since you have this too, you can also say your normal force, the magnitude of that, is equal to, one acting the opposite direction, is your weight cosine theta. All right, and we can just go up here and put that all together. So here you can say, therefore, mu is equal to, see I've got my frictional force here, I've got my frictional force here. I'm going to write it, weight sine theta over, I've got my normal force right here. That's weight cosine theta. And your weights just cancel out and you're left with sine theta over cosine theta. And I'm fine if you want to leave it that way. People in pre-cal, a lot of people may know this from just the triangle thing. Sine over cosine, that's like, what would that be? Your opposite over your adjacent would actually be tangent theta. And that's how you find your coefficient of friction, which makes sense. That's like you kind of finding your hypotenuse and your angle, and the more it's elevated, the more, I guess I should say, static friction there is. But that's how you find that.